there's another test called the second derivative test involving the second derivative, and it really relies on a notion called concavity. Okay, so we'll start off with this. So roughly speaking, concavity is when your graph looks like this. Okay, right. That's not a definition. You can't say concavity is when your graph looks like this. But that's the idea, right? This is called concave up. This is called concave down. Concave down. Okay, and so you'd like to describe this sort of thing mathematically. There are a couple of ways of doing it. We'll do a simple one. So how do we describe this? This mathematically. How do we describe this mathematically? And the thing to do is to look at the first derivative. Okay, so look at the first derivative, and what do you notice about the first derivative in the case of concave up? Don't blow it up. Would anyone like to make an observation? I see you. Okay, go ahead, Cynthia.
Well, in the first derivative, they would have a max and min, right? And it was like when it's negative before and positive after.
Okay,
And then
so the first derivative is negative before and positive after. It's negative before and positive after the extreme value. That's true. That's what the first derivative test is telling you, right? But maybe for the whole shape in general, right? Do you see some trend on the part of the first derivative tiling?
The first derivative is linear.
The first derivative is linear. Do you know that it's linear? How do you see that it's linear? I mean, in this picture, it sure looks like it might be linear, but how do you know? You don't know for sure. So yeah, I think you're thinking because it looks like a parabola, the first derivative probably is a linear function. But who knows? This may not be a parabola. This may be x to the 4 or something. Yeah, go ahead, Mahaly.
It increases.
It increases, right? So if you start from left to right, as time goes forward, you see that the first derivative is very negative to start off with, and then less negative, and then less negative, and then less negative, less negative, less negative. It becomes 0, and then it becomes slightly positive, and then more positive, et cetera, right? So the first derivative is actually strictly increasing here, and it's strictly decreasing here. Right? And that's that's the definition that we're going to use. So if you have f differentiable on AB, we say f is concave up on AB if f prime is decreasing on AB, and we really mean strictly increasing, and it's concave down on AB if f prime is decreasing, decreasing on AB. Okay, so that's how we're going to describe this mathematically. Taylor, do you have a question? Sorry.
Oh, it's just say F.
F is, sorry, that is. Okay, so there's a sort of obvious connection with F double prime. Okay. F double prime. So when is F f prime, when is f prime going to be increasing? What condition on f double prime will ensure that f prime is increasing? So, Maya? When f double prime is positive, right? We saw last time that if you have a function and its derivative is positive, then the function is strictly increasing, right? So if f double prime is positive, then f prime is strictly increasing. Okay, so that gives us a condition for concavity, right? If f is twice differentiable, if f prime is positive on AB, then you know that f is concave up, right? And if f prime is negative on AB, then f is concave down. Richka.
This is just a guess, but so does that mean that on f prime, whatever the extrema is, like whatever the extremum points are, would that be like the points where the concavity changes on the regular f graph?
Where the concavity changes, so that would say that you're saying that.
So the extrema on f prime would be the points where on f the concavity changes.
So what do you think? What do you think about that? What do people think about that?
On the curving points.
So you're saying that the concavity, if this is an extremum, then
On f prime, yeah.
of f prime.
So yeah, so if you graph f prime and if you have an extrema right there,
Okay, so this is f prime.
because like it goes from increasing to decreasing, wouldn't that be a concavity change on f?
So what? So what do you think? If f prime is a point of if f prime is a maximum for, I'm sorry, if this point is a maximum for f prime, does that tell us anything about the concavity of f? Well, let's see.
Because, right, because f prime would be, yeah, because it would be like a direction change of f prime. It means it's like
Yeah, that makes sense. That makes sense. Let me think. So, I mean, so.
And then on f double prime, it would be when the sign changes.
Hold on. So, I mean, to be sort of a stickler, it's not strictly true in the sense that, you know, you could have something that's flat, like f prime is flat here, right? And that still counts as a max.
No,
right?
right.
That still counts as a max, and this wouldn't be a point of concavity.
Yeah, no, I was just, but that would not be an extreme point. either.
But this would count as an extremum to be a stickler, right? Because they have to be, if it's greater than or equal to all other points, then yeah. So I mean, not if you throw out these guys, then okay. Yeah, good. So let's do some examples. So here's a simple one: f of x is x cubed, right? So just a simple example, right? So okay, f prime is 3x squared, right? F double prime is 6x. Right. So what do you know about the function? Where is it concave up and where is it concave down? F double prime is 6x, right? So it's something like this, right? And so you know that between negative infinity and 0, you're going to be concave down, right? And between 0 and infinity, you're concave up. And those of you who know what the function looks like, right? So this is f double prime. The function itself actually looks something like this, right? It's concave up, concave down here, and then it's concave up here. Remark points where the concavity changes, points where the concavity changes are called points of inflection. Okay. Why don't you try a harder one? So here's 15. F of x is cosine x plus x. Tell me where the thing is concave up and where it's concave down, say. Okay, so where is it? So f prime is negative sine x plus 1, and then f double prime is going to be negative cosine x. Right? So, right, so here is cosine. And so where, right? And so you know, right? It's going to be negative here, right? So it's concave down here, concave up here, concave down here, concave up here. That's it. So, it's going to be concave down here and concave up on all the other places. That's cosine. That's cosine. So negative cosine is like this. This. So where the second derivative is negative, guy's going to be concave down. It's going to be concave down here. Yeah, Rachel.
How would you break that, like a repeating function?
Yeah, sure. Okay, so you see well, let's do where it's up. Let's do where it's up first. That's probably easier. So you'd say, okay, it's going to be between 1 and 3, between 1 and 3, between 5 and 7, etc., etc. It's between odd, right? Between successive odd guys. So you'd say, okay, it's going to be like 2k plus 1 pi 2k plus 1 pi. Oh, hold on. So we want to get, it's a little bit tricky, right? Because you want to start from 1 from 1, from 5, from 9. Right. Yeah, Taylor.
Sorry, isn't that concave up? I'm just confused, because over there.
This is F double prime. Right.
Oh,
This
so
is-
the graph is about.
yeah, so F double prime is negative here. F double prime is negative here, and so the graph is the original function is concave down there.
But you drew positive cosines and negative cosines.
I drew it first, and then I flipped it over. Yeah.
Okay, so you can't just look at the graph.
Well, this is the graph of the second derivative. So
Yeah,
what
so you can look at
the thing you're looking at here is the thing that's important here is the sign. So you see it's negative here, it's positive here, it's negative here, here.
So that means,
So as for how to express it, yeah, I don't. So.
It'd be like 2k minus 1 over 2 pi over 2. 2k minus 1, so
no, plus 2k.
plus 1 over pi.
Okay, let's have a race. Whoever comes up with the right answer first, including myself, can get a point on the final or something like that, or half a point on the final. Okay, who can come up with it? Right, it's easy, right? It should be easy, right? Just not a way.
It's basically.
Right. So let's do it for the ups. Okay, for the ups. Up, Rachel.
Okay, I think I said it though. I think
Oh, yeah?
it's-
Okay.
I think for the ups, it's 2k minus 1 pi
2k minus 1 pi
over 2.
over 2.
Wait.
Yeah. 2k plus 1 pi over 2.
2k plus 1 pi.
Because then you get the 2 consecutive odd numbers pi over 2.
Is that right? So let's see. If we put in 0, then we're going to get negative 1/2, 1/2. If we put in 1, we're going to get, if we put in 1, you get 1/2, 1/2, 3/2. Right? So that gets all of them, right? That will get, if you put in 0, you get this one. If you put in 1, you get this one. If you put in 2, you're going to get this one. Yeah, so you want actually to skip them.
Okay.
Right? So it should actually be
K pi over
4, I think, right?
4.
I think it's 4. Right? Because then if you put in 0, you get negative 1 over 2, right? Negative 1 over 2, and then 1 over 2. If you put in 1, you get 3 pi over 2, 5 pi over 2, right? Et cetera, et cetera. Yeah, Dan.
This might be a silly question, but why do we need the second derivative to find your concavity when you could just plug in things into the first derivative and figure out where the slope is increasing or decreasing and do it all with that? Any sense?
Plugging into the first derivative would tell you where the slope is. Well, I mean, you'd only know that it was positive or negative, right?
So you can't just like do like, so
Like-
it's positive and then you get to your critical point and then you know it's negative, so then you know that it's concave down right there, like is that not legal?
Well, the thing is that just plugging in points, you know, maybe it gives you it's not as definite, right? Yeah. So I mean, what you're saying is that why not just check, right? As you go from left to right, just plug in some points and say, oh look, the slope f prime is getting bigger, right? But you don't know what's happening. You know, that's only at those 5 points or so, right? And so you don't have like 100% certainty. Okay, and in this case you do. Okay. So, okay. So, the application of this is the second derivative test, so classification of extrema. So here it is, that if f is twice differentiable, on AB, and C is an AB, and f prime C is 0. If f double prime C is positive, then C is a definite. If f double prime C is negative, then C is the local max. And if it's 0, then you don't get any information. Okay, so this gives us a quick way of checking if something is a local min or a local max. So let's do an example. So somebody gives you a function, 2x cubed plus 15 squared plus 24x plus 23. So maybe take a minute and look for critical points, and then we'll use the second derivative test to check what they are. Okay, so just
Wait to critical points.
yeah. So please find critical points for this guy. Take 1 minute and find critical points, and then we'll use the second derivative. Okay, so how do you find the critical points, anybody? Okay, Elizabeth, how about you?
What?
Yeah.
Yeah.
Okay, so right, so you take the first derivative, 6 x squared plus 3x plus 24, right, factor of 6, x squared plus 5x plus 4, right, so you get x plus 4, x plus 1. Right, so it's going to be negative 1. Right. And then, right, then you take the second derivative. Right, you could use your first derivative test, but we're talking about the second, so let's do it. The second derivative is going to be 12x plus 30, right? And so you see that for -4, right, you get 18, and for -1, you get for -4, you get -18, right? And for -1, you get +18. Right? And so immediately, you know that that the negative guy is going to be a max, and the positive guy is going to be a min. Right. So, yeah, sure.
Where did you put
I'm sorry. Thank you. That's a terrible mistake. Okay. So you notice that you could have done this. We could have done this just as well by using the first derivative test, right? -4, -1. If we look at the first derivative, right, it's 0 here and here, and you see this thing is a positive parabola, right? So it's going to be plus minus plus, right? So that tells you about the first function, about the original function, right? That this is going to be a max, right, and this is going to be a min. So you could have done this using the first derivative test, but instead we do something else and we say, right, somewhere around, right, at double prime crosses at negative, somewhere around here, like -30/12, right? And so, and is negative here and positive after. And so we know that -4, right, -4 is going to be a max, and 1 is going to be a min. Okay. Because it's a critical point, and the second derivative is negative. Critical point, and the second derivative is positive. So pretty straightforward, I guess. Okay, any questions about this? I know it's not the most interesting thing. Yeah, the next section, maybe we'll get to the next section, will be far more interesting. Okay, last thing I want to do in this section, why does this make sense? Why does this happen? Why does this happen? Right, you have a point. You know that the first derivative is 0 there, and you know that the second derivative. Let's do this case. You know the first derivative is 0 there. You know the second derivative is positive there. Okay. So what? So why does that make you a local min? Right? You have only 2 facts, right? F is, well, I guess you have 3. F is twice differentiable. You know that F prime is 0, F double prime is positive, right? That's all you know. So, and we're saying that makes F a min. I'm sorry, makes C a local min.
Do you prove this with math or with words?
Math words. No, you can say it in words, and then we'll translate it into math. Or I'll say it in math, or somebody will say it in math. We can translate it into words. It's all thinking. So yeah.
Okay. You can say it.
Yes. Yeah. Great.
So f prime of c equals 0, I don't have to prove that. We've already proved
Yeah,
that.
that's given to you. F prime of C. There's C. 0 there.
And if the way the slope is changing in the original equation is it's getting more positive, or
The slope of what?
the slope of the original thing. Well, f double
The
prime.
slope of F?
Yeah, so f double prime means the way the slope is changing.
F double prime is the
The rate at which the slope is changing.
at which the F prime is changing.
Yeah.
Mhm.
So if it's changing to the positive,
Yes. Yes.
then it's going to be a local max. That's the words. If it's changing for the positive, so if it's going, so f prime of c equals 0, you already know that, and that's been proven before. We don't.
Yeah, it's there.
So
Yeah,
then f
yeah.
double prime of c is changing for the positive.
Yes.
It's going from either not as positive to more positive, or
Yeah.
negative to positive. So
Well, it's going from negative to positive because it's 0.
well,
it's
either
0.
way, can it just be? It can be positive and then getting more positive.
No.
Is that not concave?
No.
Okay, well, then
I mean,
maybe-
not from this fact, right? You don't.
Oh,
we don't. We don't. We don't have.
con-
We don't have concavity. Right. We don't have concavity. Well, not exactly.
When you have f double prime.
We have f double prime is f double prime at c only. At c only.
Right.
Yeah.
Right, no, but I
Yeah.
mean, like, whatever it is, it could be from something negative to positive. If it's, the slope is changing at a positive rate.
Yeah.
Do you know what I'm saying?
Yes, but it would go from negative to positive, right? Because
Can it be
right there it's 0. Right, it's 0 there. So on the left, what is it going to be? If it's less positive than 0,
Oh, right,
it's
because
negative.
it's, okay,
Yeah.
sure, yeah. Oh, right, so then it would be, so yeah, so negative to positive.
Right, exactly.
So then,
The end.
that's words.
Yeah, that's great. That's perfect. That was great. So that was it in English. Does anyone want to? I mean, we'll just say it. You know, in math notation. We'll just write down the same thing, right? We'll just write down the same thing. So f double prime of c being greater than 0 means that f prime is increasing, right, at c. So at c, you know, f prime is increasing, so it's f prime is going to be 0, less than 0 on the left, and it's going to be f prime is going to be negative on the left and positive on the right. And so by your first derivative test, right, your function is your f prime is negative and then it's positive. So by the first derivative test, C is a min. Yeah, Emily.
What about like a tangent, or inverse, no, not tangent, when it's just like doing that thing?
This
Yeah,
one?
that, or if the slope is 0 at some point though.
Um,
And then it would work, that would be a max or a min,
so, so I think
Yeah,
let's just
that's
use like x cubed. Okay.
Sure.
X cubed is what you right. Right. At prime is the x squared. Right. At double prime is yeah. So in this case, you don't know anything. Right. That's this thing here.
So is
The
that f
sec-
double prime is 0?
F double prime is 0. Yeah.
But f double prime is 0.
F double prime is 0.
Wouldn't that just, when f double prime is 0, wouldn't that just mean it's a point of inflection where it's changing from concave up to concave down?
Yeah, but it would be a max or a min.
I think.
Well, it's still a point of
Well, no, it need not be, because you could have something, again, you could have something like this, right? And this isn't considered a point of inflection.
Couldn't you have that with just a normal thing though? Like a normal upward curve? that's
Yeah,
not
and in that case, the second derivative test wouldn't give you any,
Okay.
wouldn't give you any information, even though that would be a max.
Okay.
Yeah.
But if it equals 0, then it changes from negative to positive, then is it a point of inflection?
If the second derivative is first negative and then it's positive afterwards?
Yeah. Or either way. if it
Yeah,
changes.
yeah, that's right. Okay. Well, anyway, so this is the second derivative test. You use it to tell to tell if you're extrema or, to identify extrema. Yeah, so all of these things together, the first derivative test, the second derivative test, the first derivative and the second derivative, they give you information about the function. And it used to be that in calculus classes, everybody had to learn how to graph functions. So they'd give you some function, and then you'd spend a lot of time saying, okay, here are the zeros, here are the critical points, here are the maxes and mins. Here's where it's concave, and here's where it's convex, where it's concave up, and where it's concave down, right? And then you'd have to draw an accurate graph of the thing. Nowadays, I think that's just like a historical remnant. Right? You don't need to do that anymore. Your computers will do that for you instantly. But what's important, though, is that you understand the idea. Okay, it's important that you understand the idea. It's not necessary that you be able to graph these things. That's like doing martial arts or something. Right? It may have been useful at some point. Now it's you can do it if you like it. Or for some other purpose. Okay. Any questions about this? Okay, let's go on. Enough of that. Yeah. Okay, so the next thing is something good. L'Hopital's rule. Okay, so we're going to skip section 4.5 because we're going to skip 4.6 because that is just graphing. I don't think it has much function anymore. Now we're going to go on to L'Hopital's rule. And this answers, I think, Rachel's question about infinities. And I should say that this is actually not due to L'Hopital, but due to his teacher Bernoulli, one of the Bernoullis, and I forget which one. But something like, apparently L'Hopital paid Bernoulli for the right to use his name on this rule. And then, and so it's called L'Hopital's rule. Something along those lines. Again, the history in this class is always suspect. Okay, so here's the motivation. We're considering something like this, f of x over g of x as x approaches a point. Okay, but the limit of f of x is 0 as x approaches c, and the limit of g of x is 0 as x approaches c also. Okay? Even so, the limit could exist. The limit could exist, right? You could have something like, x as x goes to 0, say x over x, right? That limit certainly exists, right? As x approaches 0, even though the top and bottom go to 0, the thing is 1, right? So as long as you stay away from 0, you're always looking at 1. This is just 1, right? Something more sophisticated that we've seen already, the limit of sine x over x as x goes to 0 is also 1, even though the top and bottom go to 0. Right? It could exist. It also might not exist. Right? You could have something like x over x squared, right? As x goes to 0, right? Well, that's going to be 1 over x as x goes to 0, and there's no limit, right? Limit doesn't exist. Limit doesn't exist, right? Because it's 1 over x, right? As x goes to 0, the 1 over x function goes to positive infinity from the right, negative infinity from the left, right? Or you could have, something like this, x to the 4th over x squared as x goes to 0, right? Well, that's x squared, right? That's x squared as that actually exists, sorry. Sorry, let me erase that one. Sorry. Okay, in any case, there's a way of checking what the limit is. There is a way that, if it works, will tell you what the limit is. And it's this. So under certain conditions, if f and g are differentiable on AB, excluding the point C, so this slash means excluding, and the limit of f and g are both 0 as x approaches C. Then the limit of the quotient actually can be obtained as the limit of the quotient of the derivatives. The limit of the quotient actually will turn out to be equal to the limit of the quotient of the derivatives. Okay, and I should say that this could be like C could be plus or minus infinity, right? So it could be that as x goes to plus infinity or x goes to minus infinity, and you could also have you can also, this will also work in the case where the limit is plus or minus infinity. These are also possible. So, right, if your limit is plus or minus infinity and your bottom limit, if both of these are plus or minus infinity, then you can use L'Hopital's rule on it.
Wait, does it matter if one is plus and one is minus?
It doesn't. Yeah, we could have one plus or one minus. Yeah. So I'll put it like this. Doesn't matter. Okay, so let me just show you some examples. Sine x over x, the one that we took some time to show using geometry, right? If you have L'Hopital's rule, you say, oh, well, you know, both these guys are 0 over 0. I'm just going to differentiate. I get cosine over 1 as x goes to 0, right? Well, the limit of cosine as x goes to 0 is 1, right? So the limit of this ratio is the same as the limit of the ratio of the derivatives, right? As x goes to 0, and that's going to be 1. I usually put a circled H over it to indicate that I used L'Hopital's rule. That's not. You know, if you show that to somebody else, they'll say, "What is this?" But anyway, just anyway. Okay. Another example. Sine 3x over sine 2x. This is something that I think you saw in your homework as x goes to 0. Right? Both of those guys go to 0 as x goes to 0. Right? So again, you take derivatives of top and bottom. Right? On the top, you're going to get 3 cosine 3x. On the bottom, you get 2 cosine 2x. Oops, what am I saying? No, that's right. Yeah. That's right, sorry. Right, as x goes to 0, right? And so you get 3 halves. Okay. Another one. The limit of, let's do this one. Say, x to the 100 over e to the x, as x goes to infinity. Okay, we'll stop with this one, and we'll do more next time. So, what happens when you take the derivative of the top and the derivative of the bottom? Well, the top is going to give you 100 x to the 99 over e to the x, right? That's still going to be infinity over infinity as x goes to infinity. So we use L'Hopital's rule again. And we differentiate again. We get 100 times 99 e to the x to the 98, right, over e to the x. That's still going to be infinity over infinity, so we differentiate again. Right? And then at the end, what happens? the top is going to be 100 factorial, right? 100 factorial, and the bottom is still going to be e to the x. Right? Right, so you have some huge number, but it's over e to the x, and as x goes to infinity, you get 0. Right? Right. So this is another instance of seeing, maybe when you first saw the exponential function, they told you that it was fast. The exponential function is fast. This is another way of seeing it. No matter how big a polynomial I put on top, right? No matter how big a polynomial I put on top, right? As x goes to infinity, this is going to be 0. Right? E to the x beats any polynomial. Okay? Okay, we'll talk more about this next time.